Welcome everyone to our class on differential expression. We previously got our rlog counts normalized and looked at our counts. And now we're going to use that data to make some clustering of our RNA-seq data and also compare the difference between nuclear and cytoplasmic. I've always been interested in RNAs that live in the nucleus and don't go out to the cytoplasm. And we have the perfect data set to go find those. And so we'll do that. We're here at class 2023, classes 05 R analyses, RNA-seq, 01 differential expression, and Deseq 2. And I'll be running that code from my computer. But if you're here on the web at long-non-coding-rna.io/teaching, here we have a different organization of it, and that's here, and we are in the RNA-seq section here. Okay, so let's get started, and we'll need to load in our packages. We are going to need heatmap today and Deseq and ggRepel. I'm going to use my setup here in my util. Maybe I am 4 up. Okay, so I just loaded some coloring. So what we're going to do today is learn more about Deseq, and I put in some resources here. I did in the previous video on counts, and this document here is amazing. I can give you a brief overview of it here, where it's from Friedrich Dundar, and it has all the information you would need here on Deseq, such as counts data, column data, and how to generate a data set. And it goes on to talk about all these things, and also has a great section on rlog counts here, where they go through what is happening with rlog counts and what are they doing to normalize the variance based on the mean. So the higher the mean, there tends to be less variance, and that's what rlog is doing. And you can see here is an example of the raw data where they're at low values. There's a lot of variance, which can cause noise and statistical errors. And this is what the rlog transform looks like, and it's very linear between the two samples. And they go on to do more and more about this, and I think it's really worth a read if you want to dig in deeper. And we'll go over the basics as we go as well. So that's all written there. You can go check that out. And so we're just going to load our environment that we made in the previous class. Excellent. That was saved us what took a whole class, is now just loaded in our environment. And we can now make, with our sample sheet here, using our square bracket indexing that we are always using, we can go in and just get nuclear and cytoplasmic is what we're going to do differential expression on today. This could be any two conditions you have in your lab: wild type versus knockout, disease versus normal, etc. All this would apply to the same thing. And so we're going to run a filter function on our sample sheet by piping that into filter. And we're going to look for the condition column that has these names: Homo sapiens cytosolic and Homo sapiens nuclear. And we can see in our sample sheet under condition, those names are in there. Okay, so we are just subsetting out our sample sheet. I guess we're not using our handy square brackets. We could have done the same thing by square bracketing into sample sheet and pulling those out. Okay, so we now have our just nuclear and cytoplasmic sample sheet here with just our 4 observations that are cytosolic nuclear, replicate 1, replicate 2. Okay, good, that worked. We subsetted it. And now we're going to take our sample sheet sample name, and we're really just kind of checking to make sure it's in our counts as well. So in our counts, we have columns that should have the same name as that cytoplasmic and nuclear. And if that's true, then we can just go in and subset by it. Okay, so let's do that and just say sample sheet sample name column is in the column names of counts, just to be sure. True, true, true. That's good. And so now we are just turning our sample sheet nuke cyto into a data frame. Again, I'm going to go quicker for the videos so you can pause and go back, and there's text explaining what's happening as well. And we are going to make the row names of sample sheet, which currently is 1, 2, 3, and 4, not very informative. And we're going to make those the sample name from our sample sheet nuke cyto. And we can look under sample name, and that'll be the new names of our rows there. Okay, so we've just made the new row names, and they're no longer 1 through 4. They are the name of the sample. Okay, factoring, again, really important. Deseq requires this. We need to tell it which columns are the conditions we want to compare across. And so in our nuke cyto, we only have 2 conditions, really. We're going to factor our condition column here, which only has 2 different things in it. And if we make it a factor, it'll know that there's 2 entries of the same thing. If there was 3, it would know there's 3, etc. It'll take each unique key in here and make it a comparison or a factor for Deseq. So we're just going to make, and then it's important that the first one is the denominator. So if we were to compare all the samples back to total RNA, let's say, we would want total RNA to be here. And so what we're going to compare is cytoplasmic to nuclear. So numbers greater than 1 are cytoplasmic, and numbers less than 1 are nuclear, because nuclear will be in the denominator of our differential expression fold change between the samples. Okay, so let's do that, and we can write out this sample sheet since we've got it all nice and tidy, and then just load it in moving forward. Okay, so now we can see in our nuke cyto here that we have a factor with 2 levels, which is nuclear and cytoplasmic, and nuclear will be on the denominator, even though it's the first factor. So let's just see what our rlog counts matrix. Again, we took our counts, rounded them, filtered them, and ran Deseq's rlog normalization, which is in that document I was showing you. We can just take a histogram and looking at that, and what we can see is that they are fairly well normalized. There seems to almost be a second population out here, but we can see them that the frequency of them is not like very high ones taking over or very low ones, as it probably was prior. We can also look at the variance across. We just looked at a histogram with these breaks and limits. And we can also look at the variance of how much genes are changing. This is maybe a way to figure out where you want to put your fold cutoff. And we can see that at log 2, it's not that many that have that much variance in them between the samples here. Okay, so we can also look at this as an object in case you wanted to keep it. And you would then see all 40,000 genes and their variance level for each gene. So you can determine which ones are more than 1, which is sort of where the data starts to change. So we're going to actually filter on that because genes that don't have much variance aren't going to do much for differential expression. So we are taking our rlog counts matrix and we're subsetting it by the row vars that we just did here in X. And we're going to say to give us all the ones greater than 1 here is what we're doing. And this is a logical statement, but because we are indexing into the rows of the genes that are quantified are the rows in rlog counts, and we're subsetting that out. And this is going to be true and false, and then it'll only subset out the ones that are true from this object here. Okay, so now we are going to scale the counts. Our goal here, sorry, I should have mentioned, is to make a heat map. And so what we're doing is we're taking normalized samples, we're taking all of the data in rlog counts. This isn't nuclear and cytoplasmic. I guess is just an example of what you can do with rlog counts. And that's make a heat map across all the samples. And so what we're doing, what we've done now is gotten our rlog counts, filtered those that have any variance. And now we're going to do the standard thing we do before a heat map is do this, take the matrix, tip it the long way, where our tip it down, and then we're going to scale each column because the scaling needs to happen by a column, and then transmute it back to the way it was. And that scaling is going to take the mean for that column and give every value relative to that mean. So it's going to divide every value by that mean. And that's important because in each column, as it's doing the scaling, is a different sample. And so samples might have different variations. And so let's say for nuclear, we want to say on average, this is how abundant it is in the sample. How above and below the average are you within that sample? And that's kind of like a heat map in the weather, where you could say the average temperature doesn't really matter. I want to know the days it's hotter and colder in the year. And that would be a normalized value. And you can look more into this scale function, but basically we're normalizing each sample to its own mean and figuring out who's above and below the mean, just of the raw counts. We haven't done any differential expression here. Okay, so we're gonna then make it a matrix so we can put it in the heat map. And we have this scaled counts object to put in there, and we don't want to show all the gene names. And if we run this, we get a heat map. Cool. So I have a to-do there on figuring out the colors. So what we can see here now is genes that are in the nuclear fraction are highly enriched. These genes are highly enriched in the nuclear fraction. The higher the more red the color, the more enriched it is. And so again, not with differential expression, just saying where are the normalized values here. And we can see that in total RNA, there's a shared set of nuclear, which would make sense. And all of the samples clustered by their name because we fixed the sample sheet. If you didn't, you might see one of these labels swapped, and you can kind of tell that that's not the case. So what's cool about this is we basically just normalized to say the genes that are variable in this data set tend to be variable by the same type of fraction they come from. Total RNA, cytosolic, all the replicates clustered together, and that didn't have to happen. And so that's a good sign that our data is fairly coherent. And we have this cool heat map of thousands of genes. And I would be interested in figuring out what these ones are that are more nuclear than everybody else. Okay. So now we can do principal component analysis to see which samples are close to each other. The Nextflow output also did this for us using the same rlog counts. And the newer ones, pipelines do this all the time. Oh, sorry, we're using the RLD PCA function here, where we're gonna run so we're going to do principal component analysis, on our matrix, on our log counts matrix. So this is, again, on all the data, all the reads, and now it is not scaled like we just did to make the heat map. So when you do a heat map, you're going to want to scale your data. But for a PCA, you can just say, how similar are you based on the 40,000 genes we measured? How similar are the values? It's kind of like the clustering thing we did. We could make a meta plot if we wanted. So let's do that here, where we're going to run the actual statistics on the matrix. Again, we have to do this with it the long way here. And so we've left it long now. So we've flipped it so that it goes, wide. So now the 40,000 genes are the column names. And we ran principal component analysis to find out how similar each gene was in the samples, and then overall how similar the samplers were to each other. And so if we look at this RLD PCA object, we get the principal component values for each of our, should be 10 samples here, and how they compare to each other. This is similar to when we did the binary clustering of the chip data. And so we're just going to make this first as a data frame, so that'll be much easier to read. Now we can look at RLD promoter principal component analysis. And so we can see how similar each sample is in each principal component shown here. And so we're really saying is like, how many groups are there in this data here? And we're just going to move the row names out of there and make them a column. And so if we run that, we'll see them move in now as a column. Here, the values are actually in the column. And then we're going to select only principal component 1 and 2. This is saying the 2 components that explain the most amount of variance in the data, and then how similar are the samples to that variance in these 2 components, or which samples are more similar in these 2 components. As you go down in components, they have less and less information. So principal component 1 will say, these samples are best explained by these differences. And then the second component saying, then the next best thing is these components, etc. So we're just going to select those columns out and merge it with our sample sheet here. And now if we look at our principal components, we can see we have merged it with our sample sheet. So now we have this condition to plot with. And we're keeping track of all of our data. Again, that's really handy to have the MD5 sum that uniquely names this, where the FASTQ file was and what the condition was, just so you can always check if something got switched along the way, which is not uncommon. Okay, so we can just use ggplot of that data frame, and the x-axis will be principal component 1. Y-axis will be principal component 2, and we'll color by condition, so we get the color is each different type of data frame. And cool, what we can see right away is what we saw from the heat map, and with basically all of our reads. So we're just taking the normalized reads that we see samples are more similar by the fraction they were isolated from than each other. So this means these are separated by this distance of, and that's a large distance in principal component space. And in principal component 2, you see these are the most different in 1, and then in 2, these start to separate out as well. So that's a great sign that our data is correct, and we are seeing that the replicates are more similar to each other than across samples. Okay, so now we can do some differential expression. So we basically now have seen what we can do with rlog counts is make a principal component plot or a heat map, or if we want a big overview of our data, that's where rlog counts really come in handy. Now, Deseq for differential expression is going to want the raw counts, and it's going to do that normalization as it's going. And we did it before with rlog as a function, and then assay to extract those rlog counts. Now, when we run Deseq compared to nuclear versus cytoplasmic, we're going back to counts, the raw counts, and Deseq will do the normalization in the process of finding the differential expression. Okay, so we're going to just now use our handy square bracket indexing into our counts that has all the counts for all the samples. And we're going to take all the rows because those are the genes. So we want all the genes. But for the columns, we only want to take those that are in our sample sheet, nuclear, cytoplasmic. So these 4 samples here. Okay, so then we'll have just the counts for our nuclear and cytoplasmic samples. And almost always when you make something like this, you're going to want to add the row names or check them. And so I'm just checking that the row names in sample sheet is the same as the column names in the nuclear cytoplasmic. And that's important because if they're not, Deseq will be analyzing something that is called the wrong thing. So it's always worth it to check the order. And you can see we've done that every time. And the answer is true, true, true. So that's good. And then we saw in the last class that it'll automatically make an integer for us, but we can use this mode function to change the mode. We could change this to character, number, but our counts nuclear cyto right now has character values here, and we want them as integer values. And so we'll do that. And now they have changed to integer. Here we can see it's an integer of 1 through 60,000 genes, and we have our 4 rows of samples or columns of samples. So the data is really long right now. Okay, and now we're going to filter the genes out, the counts out that are 0. Again, we're not in rlogs, we're just in regular counts, and we want to take all the counts that are 0 and all the samples out. So we're just square indexing in, then doing row sum, and if it's not greater than one sample having 1 value, then we're going to take it out. And now we will do the Deseq. You can tell how important this is to make sure everything is lined up, because this is going to be the input into Deseq. So always double check, even if you just do it over here, that the column names and the row names are the same between your counts and your sample sheet. Okay, so then we're going to do this Deseq matrix, which we did before to get the rlog counts. And we're saying the count data is this matrix. Now here are nuclear cyto counts filtered. Our column data is going to be sample sheet nuclear cytoplasmic, and our design is going to be conditioned. Now we better make sure that our sample sheet nuclear cyto has a factor. Okay, we already did that. That's another good thing to always check, that the factor is in this condition column, and it's nuclear and cytoplasmic in there. And so the design is going to be based on the condition column, and that is from the call data of sample sheet nuc cyto and the counts. Okay, let's get that set up. And then that is the input for Deseq. We made this Deseq data structure, and we are just going to simply run Deseq on it using the Deseq function. Again, this happens remarkably fast considering all that is being done. And now, last time at this point, once we had run Deseq on the DDS and had Deseq DDS, so to speak, then we did rlog to normalize the counts across the samples. And now what we want to do is look at the results. So results is another Deseq function, which will tell you all the comparisons that were made. And since we only did the one, we should only have the, we can see what we got out of that is the base mean, the log fold change between nuclear and cytoplasmic, the p-value for that change. And this is exactly what you would want. If you're comparing 2 conditions, we're going to say these genes are enriched in this condition and these ones are not. We already have the answer of what genes are more nuclear than cytoplasmic inside that results data frame, which I'm just calling it res. This is something we're going to want to save so we don't have to run this again, and then we can just move forward right from here and start exploring what are the genes that are different in the nuclear and cytoplasm. And we're just going to tidy it up by making this as a data frame, and we'll call it res-df. This is probably what we would save. And we have here the gene ID, the base mean, the p-value of the fold change, and we can see some genes are so negative, meaning they're super nuclear. But what are these genes? It's hard to read this number. You could go Google it, but let's merge in our handy G2S object, which has the genes and the symbol, the gene names next to each other. And so we're just going to merge that in and add it. So now we can see our res-df has a little bit easier to read with this gene name here. And we can already start to see genes that are super nuclear would have low values because the nucleus is nuclears in the denominator. And U2 is one of the more nuclear genes there are. So this is cool. We're already starting to get good results, and we can see ribosomal proteins here as highly cytoplasmic, which makes sense. And you could spend more time looking into that. Okay, so we might want to write that out and save it for the future, because really we can go right from there and start to do a bunch of analyses, heat maps. We're going to do a volcano plot right now, which is a common thing to do, where you say the bottom is fold change and then p-value. And so what you're saying is that as you get more and more of a large differential expression, does your p-value go up? And we'll make that sort of plot here, which is very simple now. So we have our res-df, which has basically all of our Deseq results here, how much it changed, log fold to change, and the p-value are the real things we want here. And so we're going to do negative log 10 of the p-value since they're big numbers, and the same, we're going to color by the log 10 of the p-adjusted column. And the x-axis is log fold to change, and we'll just make a point plot. Excuse me. And this is what you often will see, and we could already present right away. Just by counting some numbers, we could say we have this many genes that are nuclear and this many genes that are cytoplasmic. And that's kind of interesting that it's not all the genes. So what we can say here is these we wouldn't have called significant, but these here have such high p-values and large fold changes that they're more likely to be significant. And so we've already just discovered which genes are nuclear and cytoplasmic in HepG2 and could start moving forward from there. So let's save that. And this is sort of the exploration we'll just finish on, is that if you wanted to know which gene is the most nuclear, we could do which.min on our fold change column in res-df. So we're doing which is the lowest value in this column, just another way, another fun base R command. And then index that out of the gene name in res-df. And we saw previously that that was U2, so that's cool. And we could do this with a filter and say p-value less than 0.05, et cetera, and get longer lists and get ready to go to lab meeting. I guess we will do that here. So if we wanted to go to lab meeting and say, well, these are the genes that are nuclear or cytoplasmic or different between condition A and B, is what you would still plot this same volcano plot. I guess let's look at cyto. So that is the opposite, is which.max. And then we're going to make a data frame now of nuclear genes. And so we're going to say, take our res-df and filter the log fold change for things that are less than -1. Because in log 2 space, anything less than 1 is going to be a negative number. Anything greater than 1 is going to be a positive number. And so our nuclear value is on the denominator. So most of the nuclear genes would have values less than 1 is what we would want. And so we're going to cut it off as they're at least twofold enriched in the nucleus, and that the p-value is 0.05. So now, instead of just looking at 1, we have all the nuclear genes, and there's 5,988 of them. And we've still retained all of this things. So if we wanted to see which one was the highest enriched, would go by fold change, and we see U2 there. But if we go by p-value, oh, cool. We see KCNQ10T1. We call it Knucket, and it is a long non-coding RNA that is very nuclear. So our data is looking good as we're sorting it. And so now we could cluster these and rerun many of the exercises we've had, but we can see we're starting to get some interesting data here. And then we could do the opposite for cytoplasmic, where we filter greater than 1 and 0.05. And the last thing we'll do is make an MA plot. These are good to check. Deseq did such a good job of normalizing our data, but if you're ever looking at raw counts, this is another good thing to sort of look for, is how does the fold change compare by the abundance of the gene? So the gene's really low abundance. Let's say it's 0.001 and it goes to 0.002. Well, that's a twofold change, and it might be significant, but that's like hard. That's like going from nothing to nothing. And so we're going to do ggplot, where we put in our res-df, which has our Deseq results. X-axis will be the mean of the gene, and Y will be the log fold change in nuclear versus cytoplasmic, and just do this as a geom point. And excellent. So what we don't see is that there's a bias of fold change near the bottom, and that it's pretty much a straight line. That's what we want to see, that our fold changes aren't influenced by low abundance genes, and Deseq took care of that. And this is just proof of it. And so we could save that, and then we could do this for nuclear and cyto genes separately, just by because we've made those objects where we separated out nuclear and cytogenes here. I know I have nuclear loaded, so I can do that for this here, and we can see, again, this is a bit of different axes, but the it is actually interesting that the lower valued base means for nuclear genes did have more of the fold changes. So the bigger the fold changes were down here. This one's quite interesting. That's probably U2. And we see that there are some p-values as you get into more abundant, but the more abundant you are, doesn't seem to be the case. So overall, we didn't see an issue with the data. But here in the nuclear thing, we might want to be a little careful and say, hey, we might want to filter on a base mean of like 1,000 or something, that most of these are being driven by low abundance things. Okay, so with that, let's save our environment so we can just reload it in and go on to the next class where we will compare, take what we learned here and reapply it to doing all the comparisons. So we would compare every sample back to one sample and start to look at those results in the next one. So with that, thank you and be well.